So now that we can do calculations involving humid air, psychrometric charts, or by the definitions, what types of problems does this allow us to solve as an engineer? So this is an incomplete list, but a good list, a starting point. So some problems we do are dehumidification problems. Okay? So if you have a stream of moist air and you'd like to remove some of the liquid, how can I do that? Okay, by condensing out part of the liquid. So that would mean that I would want to cool the air to drop out the liquid. Maybe I need it to go back to that warm temperature, so I might then follow up with a warming stage. But that's a dehumidification problem, taking water out of air. A humidification problem is just the opposite. I'm adding water to the air to increase the moisture content. We often do this with, sick children or something like that will blow mist of water into the air, especially in the wintertime, to help add moisture and make it easier to breathe. So how can I quantify the amount of air I need to blow in, given the temperatures that I'm involved with? What kind of relative humidity can I expect to be able to achieve by various processes? Those would be humidification problems. Evaporative cooling, we've all maybe been to an amusement park or a restaurant, especially in a desert area, where we have the sprayers that spray a little fine mist of water into the air, and it makes the air right in that area much cooler than the surrounding air. So that's an evaporative cooling problem, and the focus is on cooling the air by adding water to it. We also can look at cooling towers. A cooling tower is a simple way to take hot air off of a process and cool it down so that I've got something that is at maybe ambient temperature or whatever. Frequently used in, say, a power plant even, various things like that. So you blow air past water in order to cool the water. It's very much like an evaporative cooler, but the focus is on the water. Adiabatic mixing is when I have two streams that I mix. Maybe I have one that's dry air and one that's saturated air. If I blend them, what's the relative humidity of that final product? And if I do that adiabatically with no additional heat input, can I predict the energy? Can I predict the moisture level of the outlet air? If I know what I need for outlet air, can I predict how much of my moist air I need to bring into the process? So these are the kinds of problems that we can solve. And all we need is the information about psychrometrics. We'll need to be armed with a material balance. So we'll follow balances on dry air, and we'll follow material balances on the water. And we'll also do energy balances. So the heat transfer is the work plus the change in enthalpy, and if I have kinetic or potential energy changes. So my energy balances will also be very important here. We'll come back in future videos and look at some examples of solving engineering problems with psychrometrics.